Okay. Hi, everyone. I'm Jianshu Liu, a final year PhD student from LSU, and I'm glad here today to present my work during the internship at Globus Lab in this past summer, MoStream. It is a practice to enable machine learning guided molecular simulations on real-time stateful stream precision systems. Molecular simulations provide a powerful vehicle to explore complex biophysical phenomena such as the protein folding and how molecular behave inside batteries. For example, given a molecular, upon the molecular simulation, we can easily measure the ionization potential, which is a key property for organic electrolyte design. But conventional molecular simulations among millions of moleculars are expensive, which may lead to high computing resource usage and time-consuming human expert efforts in guiding the molecular simulation process. Emergent AI or machine learning algorithms have emerged as a particular promising route, which is to train the surrogate model and then employ the model to predict the target properties of the moleculars. However, how can we organize the machine learning guided example computations to maximize resource efficiency and provide timely machine learning guidance? Provide timely machine learning guidance becomes a key question. In Globus Lab, we have an existing project Comena, which is designed to steer the machine learning based example simulations. So in our experiments, we may see Comena coordinate the machine learning training, inference, and simulation in a sequential manner. For example, first start by training the models based on static training dataset. Second, run the inference task within a large search space, which involving 1 million moleculars from MoStream dataset. And third, after the inference, it will schedule the simulation tasks. Well, it is effective, but we still can observe the idle resource periods because the simulation task has to wait for the inference results. So our idea is that how about running these tasks in a streaming manner? So we apply stream learning that updates the machine learning model based on dynamic data streams. Compared to traditional machine learning training, the stream learning provides iterative online training based on continuous data stream. And also machine learning inferences based on a dynamic small search space can save the exploration time within the whole dataset. Moreover, it can provide timely recommendations, which can be used to guide the molecular simulations. Both academia and the industrial have made notable efforts in design practical frameworks for the stream learning. One of the important obstacles they agree is that how can we handle the runtime states? Here, our choice is to use Apache Flink. So here is our design of MoStream. First, we have a molecular generator which continuously generates a data stream of molecular messages that contains the, for example, smell string of the molecular and the ground truth IPs. And then Flink keeps consuming real-time messages, molecular messages, and process the data streams to generate ranked moleculars with high IPs. And further, it will compute the target IPs based on the using parcel to conduct the molecular simulations. Here we notice the train and the infer operator are stateful instances. So we keep a batch of moleculars as local training dataset, and also we preserve the model, updated model weights in the train operator. For the infer operator, we keep a batch of unsearched moleculars at runtime. These states will be stored embedded RocksDB state backend of Flink, and we also employ HDFS as the persistent state storage. We further deploy the MoStream on a public Cloud Lab cluster, and each node has 16 cores and 64 gigabytes memory. Here we choose to use PyFlink to enable Flink can work with the Python libraries, and also we apply Parcel to for the parallel molecular simulations. Here we evaluate the effectiveness of MoStream by measuring how many moleculars with the IP greater than 14 voltage were found over 6 hours. This figure shows the summarize the number of target moleculars we find over 6 hours. So the random means that we selected the moleculars from the whole data set randomly, and it only can identify only 2 target moleculars after 4.8 hours. Comena finds 159 moleculars, but it lacks the capability to provide real-time recommendations. So the simulation has to wait for 3.5 hours for the finish of all machine learning tasks. In contrast, our MoStream can find 165 moleculars, which is compared to Comena, but it can provide the real-time recommendations in all periods, so it can guarantee improve the resource utilization. So in this project, we currently implement the MoStream that can enable the machine learning guided molecular simulation on stateful streaming processing systems. However, we still have many things to do, such as we are going to study the novelty and the practice of MoStream in more scientific research domains. And we are also interested in optimizing the performance and the resource management of MoStream. We also believe that MoStream can serve as a good case for the research on impact of runtime states on online machine learning training. Thanks for the help and the support from Logan from Argonne National Laboratory, and also the guidance of Calchart and Ian Foster during my internship. I also appreciate some the advices from my advisor, Dr. Qian Wang from RSU. I'm available for the questions now.
Anyone got any questions? Anyone on Zoom got any questions? Oh.
Is there a project page for MoStream?
Is there a project page for MoStream?
I'm sorry.
Do you have a website for MoStream?
No, it's not yet prepared for website for public access.
Okay.
We're still working on it.
Okay. So have you published anything, or if I wanted to find out more?
It's still in progress for the submission.
Yeah. Cool. Okay. Great. Anything else?